This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is DC voltage sources in parallel circuits. Our objective is to examine electrical properties of circuits, including parallel configurations of multiple DC voltage sources. We'll examine battery bank characteristics and take a quick look at a DC power supply that allows parallel configurations. As you are no doubt aware, voltage across elements in parallel is the same. Voltage is a two-point measurement. This simple fact explains the fundamental rule regarding multiple voltage sources in a parallel configuration. The rule being this: multiple voltage sources must be of the same magnitude and same polarity when placed in parallel. Allow me to demonstrate. Consider a 12-volt battery, limited to supplying a maximum of, let's say, 2 amps of current, supplying power to a 12-volt rated DC motor that draws 1.5 amps. This is totally fine. However, let's say you wanted to run another identical motor off the same power supply. An additional 12-volt rated DC motor will draw an additional 1.5 amps of current. As a result, the battery bank needs to supply 1.5 amps plus 1.5 amps, or 3 amps. 1 amp in excess of the permitted 2 amp maximum. This is not an ideal situation, and this might damage the battery. A simple solution to this problem is to connect another identically rated 12-volt battery in parallel to the first, such that their polarities match, positive to positive, negative to negative. This collection of batteries is sometimes known as a battery bank. Key to understanding the rationale behind this approach is Kirchhoff's current law. While voltage remains the same, a parallel relationship of two similarly rated batteries can now provide twice as much current. Given each battery establishes a 12-volt differential with the same polarity, the 12-volt rated electrical loads still experience 12 volts. However, each battery can now share the responsibility of sourcing a portion of the required electrical load. Assuming equality, both batteries provide 1.5 amps each for a total of 3 amps. Thus, each battery is tasked with a more manageable current draw below the permitted maximum of 2 amps each. Beyond sharing the resultant load current, parallel arrangements of multiple batteries result in increased energy storage capacity. We'll examine the details of batteries, including discharge characteristics and charging methods in later lectures. However, let's use this simplification. Consider each battery as a finite reservoir of a given amount of energy. Let's say each battery contains 0.48 kilowatt hours of energy, or more appropriately, 480 watt hours. Given two identical batteries, this represents 480 plus 480, or 960 watt hours of energy, just shy of 1 full kilowatt hour of energy. If each battery draws 1.5 amps, an application of the power formula demonstrates that each DC motor necessitates the consumption of 18 watts of power. 2 motors means that the battery bank needs to supply 36 watts of power. My question to you is this: how long can the battery bank containing 960 watt hours of energy do so? You'll recall that energy is power times time. An algebraic rearrangement of this formula suggests that time is energy over power. Substituting our given values demonstrates that the battery bank can power these two loads for 27.6 hours, just a little bit more than 1 full day. This being said, after a full day use, i.e. 24 hours of continuously supplying 36 watts, results in the expenditure of 864 watt hours of energy of the available 960 watt hours, bringing the batteries down to a 90% depth of discharge. Such a high depth of discharge would considerably shorten the lifespan of these batteries if this occurred on a regular basis. Let's say we wanted to provide a more reasonable depth of discharge to ensure the longevity of the batteries and, in an emergency, provide at least 2 full days of autonomy for the system. Autonomy, by the way, is a measure of how long a battery bank can supply power to an electrical load without a charge. If 2 batteries in parallel can provide slightly more than 1 full day of autonomy to the system, it stands to conjecture that 4 batteries in parallel can provide slightly more than 2 full days of autonomy to the same system. This larger battery bank now contains 4 times 480 watt hours, or roughly 1.9 kilowatt hours of energy. As previously, a full day of use, i.e. 24 hours of continuously supplying 36 watts of power, results in the expenditure of 864 watt hours of energy of the available 1,920 watt hours, brings these batteries to a more reasonable 45% depth of discharge, considerably lengthening the lifespan of these batteries. You'll additionally note that 4 batteries in parallel further divides the current demanded from each battery such that each battery is tasked with a smaller 0.75 amps, or more appropriately 750 milliampere task, such that the two electrical loads consume 4 times 750 milliamperes, or 3 amps. Long story short, voltage sources in parallel increase the energy capacity of a system, and the current demanded by the system is ideally equally proportioned between each source. Let's now discuss violations of the fundamental rule of elements in parallel, this egregious violation being the parallel connection of sources with different magnitudes. Consider a freshly charged nominal 12-volt battery, presently at 12.6 volts, connected in parallel to a deeply discharged nominal 12-volt battery, presently at 10 volts. This is a bad idea under full sail, because with no current controlling element in between the two sources, consider the 2.6 volt differential across and the current through the theoretically 0 ohm wire linking the two batteries. Ohm's law demonstrates that a massive, theoretically infinite surge of current would occur between the two batteries, such that the freshly charged battery discharged into the deeply discharged battery in an uncontrollable, potentially dangerous manner. A common method of preventing this from happening is the incorporation of a semiconductor device known as a diode in series with each battery in the battery bank. We'll examine diodes in greater detail in later lectures, but for now, you can think of them as the electrical equivalent of a check valve, which is a device that permits current flow in one direction only. The arrow indicated on the diode schematic symbol indicates the direction of free flow, whereas the wall indicates the direction of no flow. Configured in this fashion, each battery in the battery bank is permitted only outgoing flow and will not allow incoming flow. This would prevent the fresh battery from discharging to the deeply discharged battery in an uncontrolled fashion. Battery banks aren't just limited to parallel configurations of single batteries. As we learned in the Voltage Sources in Series Circuits lecture, available at the Big Bad Tech channel, DC voltage sources can be placed in series aiding relationships such that their polarities mutually reinforce each other. Consider a series aiding configuration of two identical 12-volt batteries. Let's assume each battery is limited to 2 amps and has an energy capacity of 480 watt-hours. Voltage is additive and current in series is the same. This string of two 12-volt batteries can provide 24 volts and at maximum 2 amps. The string additionally represents 480 plus 480, or 960 watt-hours of energy. Let's say this doesn't cut it, and you need more current and more energy storage. Simple. Add another identical string in parallel. As a result, the battery bank can provide 24 volts and 2 amps plus 2 amps, or 4 amps of current. Given each battery has an energy capacity of 480 watt-hours, the battery bank now represents 4 times 480, or 1,920 watt-hours. You want more power and more energy? Simple. Add another identical string in parallel. What the hell, go ahead and add 2 more identical strings in parallel. This is the logic employed for remote applications like an off-grid residence or some other electrical system that needs to function without connections to the electrical grid. Long story short, the more batteries in series, the more voltage. The more strings in parallel, the more current. Finally, the more batteries in series or in parallel, the more energy storage and thus a longer autonomy period. Parallel configurations of series strings aren't limited to just batteries. Consider a solar or photovoltaic panel that produces 30 volts and 8 amps at maximum power conditions. Consider a series aiding string of 15 identically rated solar panels. This could produce 15 times 30 volts or 450 volts, and given current in series is the same, 8 amps of current. An application of the power equation demonstrates this series string could produce 450 volts times 8 amps or 3.6 kilowatts of power. If we wanted more power, we could add another identical string in parallel. In combination, the two strings would provide 450 volts and 8 plus 8, or 16 amps of current, for a total power output of 7.2 kilowatts. We'll examine solar power applications in later lectures. Alright, that's just about it for today. Before we bring this short lecture to a close, allow me to demonstrate an application of sources in parallel configurations. You'll recall the Tektronix CPS 250 triple output power supply we examined in the DC Power Supplies lecture, available at the Big Bad Tech channel, has a selector switch in the upper right-hand corner, allowing a user to choose between independent, series, and parallel mode. During the aforementioned lecture, we kept the power supply in independent mode, meaning adjustable sources A and B are electrically isolated from one another and they are independently adjustable. In the voltage sources in series lecture, also available at the Big Bad Tech channel, we flipped the selector switch to series, which stacked the A source on top of the B source in a series aiding configuration by connecting the A negative terminal to the B positive terminal. Today, let's examine the parallel mode of operation. With a power supply in independent mode, an ohmmeter demonstrates no connection exists between source B's negative terminal and source A's negative terminal. Similarly, while in independent mode, an ohmmeter demonstrates no connection exists between the source B's positive terminal and source A's positive terminal. While in independent mode, a DC voltmeter demonstrates source A is presently set at 12 volts. Similarly, while in independent mode, a DC voltmeter demonstrates source B is presently set at 8 volts. In summary, in independent mode, these are two independent and independently adjustable sources. If a user was to change the selector switch in the upper right-hand corner to parallel, the source closes two switches between the adjustable A and B source and places them in a parallel configuration such that the two positive terminals are connected to one another, as are the two negative terminals. With the power supply in parallel mode, an ohmmeter demonstrates the two positive terminals are now connected. Similarly, an ohmmeter demonstrates the two negative terminals are now connected. Besides connecting the sources in parallel, the parallel mode also hands control of both sources over to the source A voltage and current adjustment knobs. You recall, source A was presently set at 12 volts. The DC voltmeter demonstrates that the parallel configuration establishes a 12-volt differential. Using the A source voltage knob, we could adjust this from 0 to 20 volts. You'll note each source is current limited to a user-adjustable span from 0 to 500 milliamperes. If the current limitation was set to a maximum of 500 milliamperes, both sources in this parallel configuration could provide 500 milliamperes each, for a total of 1 amp. In summary, when configured in a parallel fashion, this allows a combined output from 0 to 20 volts and 0 to 1 amps and up to 20 watts. Sources are often configured in a parallel fashion to power a load together when one alone won't cut it. If only your lab partner could be as helpful. Alright, that's about it for today. In conclusion, this lecture took a look at sources and parallel configurations. Additionally, we took a quick look at battery banks and briefly examined a power supply in a parallel configuration. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.